topic is heat engines, and this is where we're going to link together the PV diagrams. Then we are going to look at actual engines that we use in real life, so comparing what we've done with a pressure volume curve to for an ideal gas compared to a real world example of, okay, what does this actually look like and what happens in an engine. Then we'll look at kind of some heat engines questions about the diagrams that we need to be looking at. So, should understand why a heat engine always wastes energy. Okay, that will be fairly clear by the end of this. Explain what an indicator diagram is and how we use it to find work done and define overall efficiency. Heat engines. All right, so when we're looking at these, there's hundreds of different types of engines. What we are going to be focusing on is called an internal combustion engine. Right, and that's what you've got up in the diagram up here. So engines are designed to do useful work. The idea is that we are able to get kinetic energy or work out of heat. So energy is transferred from kind of heat energy to work, useful energy. And for this, we need to be supplied, obviously, heat. It comes from petrol or diesel in a car engine. Plane engines and large vessels obviously use something slightly different, but the whole idea is the same. There's a fuel there that is burnt to produce some heat energy. Okay, so we're going to look specifically at petrol and diesel engines because they're what's on the AQA syllabus. Now, heat engines. You need to get very used to this type of diagram over on the right-hand side. Okay, this is really simplified. If any of you are looking at doing engineering, this is probably one of the first things you'll come across at university. So this is a really kind of key idea and layout that you should get used to. It looks simple. I dare to say that they are quite simple, but I'd also say that if you're not confident, it's quite easy to get confused quite quickly. So just to discuss what these different parts are. We have a high temperature source over here. Okay, so something that is hot at a high temperature, TH, so temperature hot. And we have heat being provided, so QH is the heat being provided into my thermodynamic system. I've then got a heat engine in the middle, which outputs two things. One, a certain amount of heat energy, so cold heat energy, or a smaller amount of colder heat energy. QC is going to be emitted by the heat engine, and there is going to be a certain amount of work that also comes out of that engine. Okay, we've got a high temperature source, which is our hot object, a low temperature sink, and sink is basically to dispose of waste energy in or dispose of heat energy in, so it's called a low temperature sink. All right. If an engine runs at a steady temperature, the internal energy doesn't change. So apart from when the engine is first heating up, it should be at a fairly consistent temperature, which means that all we're worried about is the difference in temperature between the source and the sink, which is outside. Okay, so heat transfer to the engine. So heat in is equal to the work done by the engine plus heat losses to the surroundings. Fairly straightforward. Okay, and if I express that statement in symbols, I've got the amount of energy that I put in is equal to the amount of heat energy that comes out plus the work. All right, that should be fairly straightforward. Again, this is just recapping what I've just said. So heat transfer to the engine, so that comes from my fuel, QH, work done by the engine, so it's outputting power, and heat losses to the surroundings, in which case it's normally the atmosphere that's around your engine. Okay, so expelling that heat out into the atmosphere. Fuel burning provides a high temperature source. Okay, so we've got that up at the top, and our atmosphere is that temperature sink. So we're going from petrol being burnt, petrol or diesel being burnt in the high temperature source, and that heat being released to our energy outside. Okay, next we have a steam turbine. All right, so again, this is just an example. It's something that they might ask you about, but not necessarily. But this is just to give you an idea or an understanding of kind of what is happening inside of an engine. So steam turbine kind of counts as a heat engine. If we've got a steam turbine, we burn our fuel and we heat up the water. All right, so we're adding a certain amount of heat to that object. Our high pressure steam is then forced through a turbine, and it forces that turbine to turn round. Okay, and that is transferring that energy into work. All right, so the spinning of that turbine is kinetic energy. We've kind of covered the rotational energy, the rotational kinetic energy in the rotational dynamics question, so they can link this to the rotational dynamics as well. So high pressure steam goes around and it causes a certain amount of work, and obviously when my turbine turns, it turns my generator. Then, now low pressure steam, because it's lost its energy, it's done a certain amount of work and it's now lost energy, that steam is then cooled down in the condenser and it takes QC of heat out into the cold water sink. Okay, so we lose a whole load of energy when we cool it in the condenser. Now, what would happen if we didn't put the steam through the condenser? You might be thinking, right, well, why do we cool it down when we get to the condenser? Okay, why do we waste that energy? Why do we just not put it straight back in? But there's a very good reason that we don't do so. Okay, if the low pressure after the turbine, if we didn't cool it down, we would end up with a fairly high pressure after that turbine. So pressure after the turbine would rise because we're not cooling that water down, and therefore it's still got lots and lots of energy. And eventually the steam wouldn't flow through. Now we know that energy only flows from hot to cold. Okay, there has to be a difference in temperature in order for heat energy to flow between two objects. If two things are the same temperature, the heat doesn't transfer between them. So we need a difference between the hot and the cold in order to force the energy to move from the hot area down to our cold area. All right. So our condenser, the low temperature is essential if we want that energy to continue moving from our hot bit over here through our turbine into our cold or low temperature sink. All right. If these two things were the same temperature, the steam wouldn't move anywhere. Okay, so we need a difference in order to create that movement of energy and of the steam itself. And this is true for any heat engine. I've shown you a steam turbine, okay, because it's a fairly simple example. We're now going to look at a turbojet. All right, so this is the kind of things that you get on a plane, right, when you're looking out the window and you go on your holiday. All right. Air intake, we compress it in a compressor. Okay, so we put the air that flows into the front, we force it through these turbines and we compress it. All right. And by compressing it, we are going to heat it up. We then also heat it strongly. So we mix it with fuel and we burn that fuel off and heat that air up. Okay, really, really quickly. Then we have a very hot air forcing out of the exhaust. Okay, so we've got something that comes in at a relatively low temperature. We compress it, we heat it, so it's high pressure, and that is ejected out of the back of my engine. All right, and that causes a force in the forward direction. Now, the fuel supplies the energy for the work to be done. If we weren't heating it up, there wouldn't be a great big difference in temperature, and therefore the air wouldn't fly out the back. Okay, we would have no power being delivered by that engine. All right, but the hot air from the exhaust transfers that energy to the atmosphere. So we're losing that as our cold temperature sink. So fuel burning supplies my high temperature source. Okay, that's my energy in, my hot source. And then the atmosphere, when it flies out the back, is a low temperature sink. So if we go back to that kind of diagram that we had before, this is the input. Okay, we have the output, so waste energy, and then the work that's being done is the rotation of these turbines on the way out, which forces our object forward. Now, why can it never be 100% efficient? So let's think about this. Why is it that a heat engine can never be 100% efficient? If we are using heat transfer, okay, we have to have a low temperature sink to move that energy out of the source. As I said a minute ago, if two things are the same temperature, we don't have a movement of energy from the high temperature to the low temperature. All right. In order to make that happen, in order for the energy to be withdrawn from my high temperature source, there has to be a difference in temperature. All right. So the work done can never be equal to the heat transfer, because if there's no heat transfer, there's no movement of energy between those two. All right. So this is this is the second law of thermodynamics. All right. And it's impossible for heat transfer from a high temperature source to produce an equal amount of work. So I can't take all of that energy out of a hot object and manage to get it all to convert into work, because I need a cold temperature there in order to draw that energy out. Okay, if there's no cold temperature, then it's no good. Our first law of thermodynamics obviously tells us that we can't get more energy out than we put in. Okay, we had that equation of heat is equal to change in internal energy times work. So we can't get more work out than we have heat going in. All right. So the first law was a fairly simple one. The second law goes further in saying that useful energy is always less than the energy put into a machine. Now, that won't come as a surprise to you. All right. If you've got useful energy, you're always going to get less energy out than you put into a machine. That's fairly straightforward. If we look at efficiency, again, no real surprises here. So efficiency of an engine is defined as the work done by the engine over the energy supplied by the engine. All right, and if we want to turn that into a percentage, obviously we've got to multiply that by 100. Now, here's where we link this idea together, because these efficiency equations won't be a particular surprise to you. Now we're going to link in what we've just learned about heat engines. So a heat engine has a percentage efficiency of the work done by the engine. Okay, that was the work done that we get out over the hot energy that we put in, or the heat energy that we put in, okay, multiplied by 100. And that's work done by the engine. Right? So we've got work divided by heat energy gives me my efficiency. We always know that the amount of work that we're going to get out is going to be less than the energy that we put in. Okay, so we're not going to have an energy or an engine that can produce 100% efficiency, or actually anywhere near. Okay, what would happen if this wasn't the case? Well, let's have a look. So if that wasn't the case, if work could be the same as QH, there would be no heat transfer to the low temperature sink. All right, so all of this QH would be transferred into work. Now, because then everything would be the same temperature, everything would be at that temperature TH, we would actually have no transfer of energy. Okay, we have to have a temperature difference in order to make that happen. I can't stress that enough. So that's why engines necessarily, to function, an engine has to be inefficient. There has to be a difference, and there has to be some wasted energy that comes out to that low temperature sink. All right. Without any heat transfer from the source, the engine wouldn't work. So we're going to have to do that. Now, some of you may well have heard of this guy before. Okay, again, if you go on to do mechanical engineering or anything of that nature, you will definitely study the Otto cycle. All right, Nicholas Otto, 1876. Okay, technically, okay, this is the proper name for it is a 4-stroke engine cycle. You get 2-stroke engines and 4-stroke engines, and we'll go into why this is called a 4-stroke engine in quite a lot of detail. Technical term, 4-stroke engine, but it's also referred to as the Otto cycle. Now you'll see this movement on the right hand side. It's kind of a simplified version of an engine kind of internally. All right, and we've got the Otto cycle is an idealized form of that cycle. Right, now this is what you get in your standard car. Okay, so if you're looking at a petrol car, or to be fair, diesel cars, so petrol cars predominantly, you're looking at a 4-stroke cycle. It's called 4 strokes because the whole process takes 4 strokes of this piston moving up and down. So we have a cylinder, okay? We've got a piston that is moving up and down. We've got an inlet valve, okay? So this is our air and fuel mix that comes in. We've got a spark plug. So this part is our spark plug. That's kind of there to ignite everything. And we have an exhaust valve that comes out on the far side. What you will see also down here, so linking it back to that rotational dynamics, you've got a semicircular flywheel. This is your crankshaft. So there is a little bit of a flywheel in there. And we've got that connected to a camshaft, which controls our valves. All right. Now, we need to understand the indicator diagram. Okay, so again, that PV curve or PV diagram, it's called an indicator diagram for the Otto cycle. So this is an ideal Otto cycle. And one of the big kind of questions that we have at A level is they might give you an idealized Otto cycle versus a real life Otto cycle. So you can actually measure these indicator diagrams for real engines, and they often talk about, or they ask you to explain the differences between the theory, what we see here, and the reality, which we'll look at a little bit later. So 4 strokes of the cycle: intake, compression, power, and exhaust. When I was at university, they taught us this as suck, squeeze, bang, blow. All right, so intake is drawing in an air fuel mixture. Compression is squeezing that into a small space, so you increase that pressure. Then you ignite it and you get your power stroke where the piston is forced back down, and that's what creates your engine or keeps your engine running. That's what you're aiming to do. And exhaust is to get rid of all of the burnt gases and fuel out to restart the process. Okay. Each corresponds to 1 full stroke of the piston. All right, so we need 2 revolutions of this crankshaft in order to complete it. Please be really careful. There's a really common mistake that I'll talk about in a minute. They sometimes tell you the revolutions per minute of a crankshaft, and you've got to realize that 2 revolutions is 1 cycle of this, because the piston has got to go up and down twice. All right, so I'll show you some of those questions a little bit later on. Right. Induction stroke. So this is the intake stroke, essentially. In order to make the stuff, the air fuel mixture come into this cylinder, okay, my piston moves downwards and it creates a pressure that is just below atmospheric pressure. Okay, by moving downwards, it's expanding, it creates a bit of a vacuum, and that creates a pressure below atmospheric pressure. And we know if the pressure outside is higher than the pressure inside my cylinder, we're going to get our flow of air moving inwards. Okay, so what we have is moving from a small volume to a large volume, all right, of my fuel air mixture that's coming in. So it's my induction stroke or my intake stroke. I've then got a compression stroke. Okay, so if we're following on our PV or indicator diagram down at the bottom, this is dragging my air into my cylinder. And then what I'm going to do is compress it. Okay, so adiabatic compression. Now it's adiabatic. Let's think about why it's adiabatic and not isothermal. It's adiabatic because this happens very, very quickly. There's not time for the heat to transfer out. So this is happening. It can happen, 20, 30, 40 times a second quite comfortably. So this is adiabatic because there's no room for or no time for that heat to escape. As the piston rises, as my piston comes up, I've got a nice full piston full of, or nice full cylinder full of air. My piston moves upwards and compresses all of that air into a much smaller space. Okay, and my valve closes because obviously it's being pushed upwards. If we look at our diagram here, we have volume decreasing and pressure increasing between 0.2 and 0.3. Okay, so my compression stroke 2 to 3, volume decreasing, pressure increasing. This is where we have our flywheel helping us. So flywheel momentum drives that piston upwards. Okay, because we need to provide work to do that job. Okay, if we didn't have any energy in order to actually compress it, we've got to put some energy in, and that energy is given to us from a flywheel. All right, so that compresses my fuel and air mixture adiabatically. Think quite carefully about what's going to happen here. If I'm compressing it adiabatically, we've got no heat transfer. I know that the internal energy of that gas is going to increase. So therefore, the temperature of that mixture is going to increase. All right, happens quickly, so there's no time to leave. That's why it's adiabatic. And therefore, my temperature is going to rise to about 300 degrees. So even though it comes in at kind of normal atmospheric temperature, probably room temperature, maybe a little bit warmer because it's near the engine, it rises very quickly due to that compression. Once we are there, okay, so we have our nice compressed air ready to go, it's the idea of ignition. So from here, we have our spark plug doing the job of igniting this idea, or igniting that fuel air mixture. All right. Now the spark plug provides obviously a spark that ignites that fuel and air mixture. Okay, the timing of that spark has to be perfect. Okay, and we want it to ignite just as that gas is about as compressed as possible. That's how we're going to get the most work out of this. So what we want is an ignition, and where the temperature shoots up because of the ignition, we obviously have a fixed volume at this very top section. So fixed volume, when it's at this top dead center position, the spark plug ignites and sets light to the fuel, which causes a rapid rise in pressure. So that fuel causes the temperature and pressure to increase massively. All right. That, linking back to our heat engines, is where the heat comes from. So the heat released by the burning of our fuel at that point is our input amount of heat. So we've got temperature and pressure to rise very rapidly because we've just put heat in. So this section 3 to 4 is where we have the burning taking place. Now, power stroke. Now that I have a very high temperature, high pressure gas within that piston, okay, it's going to expand. We've got a very, very high pressure pushing down on this piston, and the air or the fuel mixture, fuel and air mixture, is going to expand adiabatically. So the high pressure forces that piston downwards. So what we're seeing here is that piston is forced downwards by a huge pressure. Shouldn't be a surprise. As it expands, the volume increases and my pressure decreases. Okay, because it's the gas is doing work in order to push that piston down. So my gas expands, therefore my pressure and temperature are both going to decrease, and that's what I can see on this diagram here. Okay, so we're quite a way through now. So we've got our power stroke that kind of comes out. That's what's providing the energy to propel the car along the road. And finally, we've got our cooling section to take us back down to our start. When our exhaust valve opens, all right, the leftover pressure, it's a very high pressure inside the cylinder and obviously atmospheric pressure outside. So very quickly, lots of this gas will leave. The piston also then travels upwards to force out all of that air fuel mixture. You don't want any air or fuel left in there before the beginning of the next stroke. All right. So at the bottom of the power stroke, exhaust valve is open and most of the gas rushes out. Okay. That's my dump of energy that is coming out. So for my heat engine, that's my low temperature sink, the amount of heat that I'm sending over there. And the pressure and temperature obviously decreases because we're releasing that pressure, we're releasing that gas that's burnt out and it's being forced outwards. Okay. So that's cooling. And then we've got our exhaust stroke. Let's just be absolutely clear here. This cooling is this drop along this right hand side. So as that valve opens, it cools very, very quickly to drop back to here. Okay, but I'm still at a large volume. I'm still at that large fixed volume. It's almost an instantaneous change down to back to that point. And then we get to the exhaust stroke where my piston is going to come back up and force the gases back out. All right. So the upward stroke drives out anything there. Obviously, if the fuel is burnt, it's pointless. All right. And then our cycle starts again with our intake stroke. So once it's exhausted or pushed out all of the gases, we then have our intake stroke that comes back in. So we have a nice kind of cycle that's going through. All right. So again, we've got our diagram on the right hand side. We've got 4 strokes of the piston, hence a 4-stroke engine. Fuel is burned inside the cylinder, and it's referred to as an internal combustion engine because this is happening inside of the cylinder or internally to the engine. And we've got expansion and compression of the gas at adiabatic because it's high speed. If we look at the reality, an actual petrol engine is far less efficient than the Otto cycle. All right, and there's a few reasons for this. We're going to look at it in a minute. Because the working substance, number one, isn't an ideal gas. Okay, we don't have that assumption that, number one, the molecules are interacting with each other, unlike an ideal gas. Okay, so we assumed with an ideal gas that they don't interact. In fact, they do. They exert potential energy or pressure on each other. Okay, so we obviously get a little bit less efficiency than our perfect diagram. In fact, if we look at this, this is the kind of shape that we can expect for a measured indicator diagram. So these are very, very common. If you go into the world of motorsport, if you go into the world of being a mechanic, okay, they understand the indicator diagrams. We've got a theoretical diagram here, and then we've got a real measured indicator diagram, okay, and we call this an indicator loop because of the enclosed space, the closed loop in there. We see that less and less work is done because we've got a smaller area enclosed than we do in our theoretical loop. All right. We don't have these sharp corners. Okay, we have rounded corners on here because the valves aren't opening and closing instantly. In order for this pressure to jump very quickly, or in order for this pressure to drop, I would have to have an instantaneous valve. And in reality, that doesn't happen. Okay, so we have a valve opening. It takes a little bit of time to open and a little bit of time to close. So therefore, there's a kind of rounding to this issue. You'll also see a rounding of this corner here because the timing of your spark, again, the ignition process isn't instantaneous. So the fuel will start to burn, okay, a little bit before it hits that top dead center position. So where that piston is right at the top of the cylinder. Okay, so we're up at that point there. Maximum temperature isn't reached because it's not perfect combustion. Okay, you're not going to get all of that energy out of that gas. It's not going to be perfect. And we also know that expansion and compression is not going to be perfectly adiabatic. Okay, you are going to lose some energy into the piston or the cylinders itself. Okay, and that's why your engine gets hot as it goes along. Okay. Well done for getting this far. There's a huge amount of information there. I'm going to pause this video so that you can kind of come back to it a little bit later on. Okay, if you need to use this video, I will leave it up and available so you can keep coming back to it as we go through. Okay, if you're ready, you can move on to the next one.